Welcome back to the Deep Dive. We're continuing our journey through the online encyclopedia of integer sequences, focusing today on, well, a sequence that's just absolutely fundamental if you're digging into number theory. That's OEIS A000203.
It really is a cornerstone. A000203 gives us an defined as sigma n, and sigma n is simply the sum of all the positive divisors of n. That includes 1, and it includes n itself.
Right.
You'll sometimes see it written as sigma subscript 1, so sigma 1 n.
That means sigma 1.
And today, our mission is basically to unpack this, look at the definitions, some key properties, and really get a feel for why the sequence, which sounds pretty simple on the surface, is actually so significant.
Okay, let's start right there. Sigma n, sum of the divisors. Can we just walk through a really basic example, like what about n equals 6?
Good place to start. For n6, the positive divisors are, well, you've got 1, 2, 3, and 6 itself.
Right.
Add those up. 1 plus 2 plus 3 plus 6. That gives you 12. So sigma 6 is 12.
Yeah.
Simple as that.
Okay, 12. Straightforward. Now, when you look at the OEIS entry, it immediately points to related sequences. There's sigma n and also something called the aliquot sum, deficient. How do these fit in or differ, I guess?
That's a really good point to clarify early on. Sigma n, that's sequence A000005 in the OEIS, isn't about summing, it's about counting. It tells you how many positive divisors n has.
Okay, the count.
Exactly. Then the aliquot sum, SM, which is A001065, is the sum of the divisors excluding n itself, so just the proper divisors.
Right, excluding n.
Let's take n12, maybe.
Right.
The divisors are 1, 2, 3, 4, 6, and 12.
Okay.
So sigma 12, the count is 6. There are 6 divisors. Sigma 112, our main sequence today, is the sum. 1 plus 2 plus 3 plus 4 plus 6 plus 12. That adds up to 28.
28, got it.
And then the aliquot sum, S12, would be just the sum of the proper divisors. 1 plus 2 plus 3 plus 4 plus 6, which is 16. Or, simply sigma 112 minus 12. So 28 minus 12 is 16.
That makes sense. Count, sum of all, sum excluding the number itself. It helps to see them side by side. Okay, let's dig into sigma itself. A really important property mentioned is that it's a multiplicative function. What does that actually mean for us?
Yeah, multiplicative. This is incredibly useful. It means if you take two numbers, let's call them A and B, and they don't share any common prime factors, their greatest common divisor, GCD, is 1.
They're coprime.
Exactly, coprime. Then sigma of their product, sigma ab, is just sigma A multiplied by sigma B. You can calculate the sigma for each part separately and then just multiply the results.
Okay, that sounds handy for calculations.
Yeah.
Does it tell us something deeper, though?
Oh, absolutely. It's fundamental because it lets us compute sigma directly from the prime factorization of n. Any integer n can be written uniquely as a product of prime powers, right? Like p1 to the power a1 times p2 to the power a2, and so on.
Standard prime factorization.
Precisely. Because sigma is multiplicative, sigma n will be the product of sigma applied to each of those prime power components. So it's sigma p1a1 times sigma p2a2 times. You get the idea.
Okay. And what's sigma of a prime power, like sigma pa?
Well, the divisors of pa are just 1 pp squared all the way up to pa.
Right.
So sigma pa is just the sum, 1 plus p2 plus pa plus pa.
Okay, so sigma n is a product of those sums, one for each prime factor.
Sure.
That still feels like it could be a bit messy to calculate if the powers are large. Is there a shortcut for that sum?
Yes, there is. That sum, 1 plus p plus t2 plus pa, is a geometric series. And there's a very nice closed formula for it. It equals p to the power of a plus 1 minus 1, all divided by p minus 1.
The geometric series formula.
Exactly. So to get sigma n for any n, you find its prime factorization, say n equals p1a1, p2a2, then sigma n is the product for I, from 1 to r, of these fractions, pi I plus 1, pi 1.
Let's try that on our n12 example again. 12 is 2 squared times 3 to the power 1.
Perfect. So using the formula, for the 22 part, we get 2 plus 1, 2, 1. That's 23, 1, which is 8, 1 equals 7.
Okay, so
For the 3, 1 part, we get 3, 1 plus 1, 3, 1. That's 32, 1, 2, which is 9, 1, 2 equals 8, 2 equals 4.
Right.
And since sigma is multiplicative, sigma 22, sigma 31, 4 equals 28.
Which is exactly what we got just by summing them up earlier. Much cleaner with the formula, especially for bigger numbers, I imagine.
Definitely. That multiplicative property and the resulting formula are workhorses in number theory.
Okay, so that's a core property.
Yeah.
But the OEIS entry, like you said, hints at broader connections. Sigma isn't just about primes and divisors in isolation, is it?
Not at all. One of the oldest connections, going way back, is how sigma relates to classifying numbers. Perfect numbers, abundant numbers, deficient numbers.
Ah, yes, the Greek classification.
Exactly. A number n is called perfect if the sum of its divisors, sigma n, is exactly twice the number itself, 2can. If sigma n is greater than 2can, it's abundant. If sigma is less than 2can, it's deficient.
Like 6 is perfect because 6 plus 6 is 12, which is 2 times 6. And 12 is abundant because sigma 12 equals 28, which is more than 2 times 12.
Precisely. And these classifications, defined purely by sigma, lead to fascinating questions like, are there any odd perfect numbers? Still an open problem, believe it or not.
Wow. Okay, that's a classic link. But the entry also mentioned connections to lattices and group theory. That feels like a different world entirely.
It does, doesn't it? But it's true. Here's a rather unexpected one. Sigma n counts the number of sublattices that have index n within a standard two-dimensional integer lattice, like z cross z.
Sublattices, so like sparser grids within the main grid.
Kind of, yes. Imagine the standard grid of points with integer coordinates. A sublattice of index n is basically a grid generated by two vectors, such that the area of the parallelogram they form is n times the area of the basic unit square. Sigma tells you how many distinct ways you can form such a sublattice.
That's surprising.
Isn't it? And there's an equivalent group theory interpretation. Sigma n is also the number of subgroups of index n in the group ZXC, the direct product of two infinite cyclic groups.
Yeah.
And maybe even more concretely, it's also the number of subgroups of order n in the group CNXCN, which is the direct product of two cyclic groups of order n. It's quite remarkable that summing divisors relates to counting these kinds of algebraic structures.
Truly remarkable. It really connects different areas. Are there other surprising places sigma shows up?
Well, there's a connection to p-adic numbers, too.
Okay, now you're really stretching things.
Hey, maybe a little. But if you take a prime p that's larger than n, sigma n actually counts the number of field extensions over the p-adic numbers qp that have degrees n, sitting inside the algebraic closure of qp. It just keeps popping up.
It really does. It seems woven into the fabric somehow. The OEIS page also mentions an Euler recurrence relation. That sounds more computational again.
Yes, Euler found this ingenious way to calculate sigma using values of sigma for smaller numbers. It involves summing terms related to sigma n, where the k values are the so-called generalized pentagonal numbers.
Pentagonal numbers,
Yeah.
like 1, 5, 12.
Those are the regular ones. The generalized ones include values like 3i2, i2 for both positive and negative integers I, so you get 0, 1, 2, 5, 7, 12, 15, and so on. The recurrence is sigma n equals a sum involving alternating signs in terms like sigma and pi, where pi are these generalized pentagonal numbers. It's quite elegant, actually.
Interesting, a recursive definition. What about simpler properties? Like,
Yeah.
when is sigma itself an odd number?
Ah, yes, there's a straightforward condition for that. Sigma n is odd if and only if n is a perfect square or twice a perfect square.
Okay, so nk2 or n equals 2k2.
Exactly. You can figure that out by looking at the formula sigma product of PA plus 1 to 1 and thinking about when each factor in that product is odd.
Makes sense. And now, the really big one, the connection to the Riemann hypothesis.
Yes. This is arguably the most profound connection. It links this seemingly elementary function, sigma, to one of the deepest unsolved problems in all of mathematics.
How does that work?
In 1984, Geoffrey Ligarius proved that the Riemann hypothesis is actually equivalent to a specific inequality involving sigma. The statement is that the Riemann hypothesis is true if and only if sigma is less than hn plus xphn, log hn, for all n greater than 1. Here, hn is the nth harmonic number, 1 plus 12 plus 13 plus 1 plus 1.
Wow. So understanding the upper bound of the sum-of-divisors function is essentially the same problem as understanding the distribution of prime numbers.
In a very precise sense, yes. It transforms the Riemann hypothesis from a problem about the complex zeros of the zeta function into a statement purely about the growth rate of sigma. It's absolutely stunning.
That just elevates sigma to a whole new level. Okay, shifting slightly, the OEIS page also talks about connections to different kinds of mathematical series, Dirichlet series, Lambert series.
Right. These are powerful tools from analytic number theory used to study the properties of arithmetic functions like sigma. The Dirichlet series associated with sigma, which is the sum of divisors raised to the power has a particularly beautiful form.
Okay.
The sum from n1 to infinity of sigma divided by n turns out to be equal to the product of the Riemann zeta functions zeta s and zeta sa, provided s is large enough.
So for our sigma 1, we're A1.
For our case A11, the Dirichlet series sum sigma 1 nns is exactly zeta ss times zetas on 1. This relationship is incredibly important for studying the average behavior and analytic properties of sigma.
And there's a similar structure for sigma n of the divisor-counting function.
Yes. For sigma 0, often just written as ds and ns, the Dirichlet series sum d and ns is equal to zeta s squared, so zeta zeta. These connections to the zeta function are really fundamental.
What about the Lambert series mentioned?
Lambert series are another type. A typical form is summing qn times sigma n from n or 1 to infinity. These often appear in combinatorics and the theory of partitions. There's an identity relating this sum to another sum, the sum of na qn, 1qn. These series provide different analytic perspectives on the function.
So these series essentially encode the sequence's properties in a way that allows for powerful mathematical analysis. Okay, finally, let's touch on how fast sigma n actually grows compared to n.
Good question. We know sigma n is always greater than n, since n itself is a divisor. But how much greater can it be? Grunwald's theorem from 1913 gives us insight into the maximum growth.
What does it say?
It tells us about the limit superior. The lim sup of sigma divided by n log n as n goes to infinity is equal to e to the power of gamma.
Right.
Here, gamma is the Euler-Mascheroni constant, about 0.577.
Log n. It grows very slowly, so sigma n doesn't usually get that much bigger than n log n.
On average, no. But it can occasionally reach peaks proportional to n log n, and the constant E gamma tells us the precise scaling factor for those peaks in the limit.
And this also ties back to the Riemann hypothesis, doesn't it? Through Robin's theorem.
It does indeed. Guy Robin, also in 1984, showed that the Riemann hypothesis is equivalent to the inequality sigma being strictly less than a gamma n log n for all n greater than 5040.
Wait, for all n greater than 5040, why that specific number?
Because there are actually known counterexamples to that inequality for some smaller values of n. The largest known integer n, for which sigma is not less than a gamma n log n, is precisely n equals 5040. Robin proved that if the Riemann hypothesis is true, then 5040 is the last violation. If RH is false, there would be infinitely many violations.
So checking that inequality for large numbers is another way to test RH.
Effectively, yes. Though proving it holds for all n 5040 is the hard part, equivalent to proving RH itself. It just beautifully illustrates again how deeply connected sigma is to these profound questions.
It's incredible. So summing up, we started with what seems like a very basic idea. Add up the divisors of a number. But it turns out this simple operation defines a function that's multiplicative, has formulas tied to prime factorization, connects to classifying numbers, pops up unexpectedly in lattice theory and group theory,
Empathic analysis.
has elegant series representations, and most strikingly, holds information fundamentally equivalent to the Riemann hypothesis regarding its growth rate.
You got it. It's a perfect example of how seemingly simple concepts in number theory can have incredibly deep roots and far-reaching branches throughout mathematics.
For anyone listening, seriously, go explore OEIS A000203. The entry itself is a gateway, full of formulas, references, links to related sequences. It really drives home how much richness is packed into this one sequence.
Absolutely. It's a fantastic starting point for exploration. And maybe it leaves you, the listener, with this thought to ponder. How can the simple act of considering the divisors of a number, something you learn early on, ultimately contain keys to unlock some of the deepest, most fundamental secrets about numbers themselves? It's a question that keeps number theorists busy, that's for sure.